Hi, welcome to the channel Friend for Maths. This is the part 5 video of chapter 1 real numbers, and in this we are going to discuss the topic revisiting irrational numbers. Okay, and we can go through some basics. Here, what is the co-prime numbers? What is co-prime numbers? We are taken any two numbers and they have no common factors to each other than the number 1, then they can be called as they are co-prime to each other. That is, the number 1 is a factor of every numbers. Okay, so they are it is a common factor of every number, but other than this number 1, if they have no other common factors, then these numbers can be called as the co-prime to each other. We can take an example, 21 and 22, and the factors of 21 are 1, 3, 7 and 21, and factors of 22 are 1, 2, 11 and 22, and look at their common factors. Here number 1 is a common factor, but no other common factors to each other. Then we can say that these 21 and 22 are co-prime to each other. Okay, we can go to next example, 21 and 24. Here 21 have the factors 1, 3, 7 and 21, and 24 has the factor 1, 2, 3, 4, 6, 8, 12 and 24, and look out their common factors. Other than 1, they have 3 also their common factor. So here we can say that they are not co-prime because they have a common factor 3 other than the number 1. Okay, next we know that what is a rational number. Rational number is a number which can be expressed in the fraction form, that is p by q form, with a numerator and a denominator, where this p and q are integers and this numerator, which is q, is not equal to 0. Okay, then what is an irrational number? Rational numbers are those numbers which are not rational, that means which cannot be expressed as the fraction form with the p by q, p and q are some integers, and okay, and q is not equal to 0. Such numbers can be called as irrational number. Understood? Okay, next we can go to the topic revisiting irrational numbers. Under this topic there comes two small theorems. Okay, first theorem is this, that is, taking a number p and it is a prime number. Okay, and this, if p divides a square, a is a positive integer. Okay, and this p, which is a prime number, that divides a square, then p will divide a also. That is the theorem. If p divides a square, then p divides a also, and we have to prove that. Okay, from this we can understand that if p divides a square, that is p is a factor of a square. Okay, remember that. And also, if any positive integer can be written as the product of its prime factors through prime factorization method, we know that. So here a will be the equal to the product of its prime factors p1, p2, etc. up to pn. Okay, where these are the prime factors of a, and we are squaring this a, that is, here we get a square is equal to p1, p2, etc. up to pn into p1, p2, etc. up to pn, the same thing. And from this we can take what a square is equal to this, then this p1, p2, etc. up to pn is the only prime factors of a square. Okay, if these are the only prime factors of a square, and we have here that p is also a factor of a square, then from these two cases we can say that this p belongs to this group. P will be definitely belongs to this group. If p divides a square, p also a factor of a square. And if this p belongs to this group, what is this p1, p2, etc. up to pn? That is actually a. isn't it? If A is equal to this P1, P2, etc. up to Pn, that means this P also divides A, because this P belongs to this group, that is P divides A also. Okay, that is the proof. Here we have proved that as A is equal to P1, P2, etc. up to Pn, and we get that P belongs to this group, and definitely then P will be divide A also. Okay. Next theorem is to prove that root 2 is an irrational number. This is the theorem. Root 2 is an irrational number, and we are going to prove that. And to prove that, we are first assuming in a wrong way, that is a wrong assumption, that root 2 is a rational number. If root 2 is a rational number, it can be written as the form P by Q form, and here we are taking R and S some integers, and root 2 is equal to R by S, and we are saying that this R and S has common factors other than 1, and we are taking that common factor and we are cancelling this R and S, and we are getting after cancellation some other two integers. Here root 2 is equal to A by B. Here this A and B have no other common factors other than 1, that is here now A and B are co-prime. Okay, and next we are going to this equation, taking B here, B root 2 is equal to A, and squaring both sides. Okay, when squaring root 2, what we get? 2. Okay, here 2b square is equal to a square, and look at this. If 2b square is equal to a square, that means 2 divides a square, that is 2 is a factor of a square. If 2 divides a square, then 2 divides a also, from the theorem, first theorem. Okay, and if 2 divides a, that is 2 is a factor of a. Okay, and now we are writing a as the multiple of 2, that is a is equal to 2c, where c is some integer, and substituting this value of a equal to 2c here in this equation, we get 2b square is equal to 4c square. Okay, and cancelling this 2 and c, we get b square is equal to 2c square. And look at this, from this we can get that 2 divides b square, that is if 2 divides b square, 2 divides b also, from the theorem. Okay, and if 2 divides b, that means 2 is a factor of b, and what we get here, 2 is now the common factor of a. Okay, but we have here that they are co-prime to each other and they have no other common factors other than number 1. Why we get like this? That is because of our wrong assumption, that is root 2 is a rational number. That was our wrong assumption. That is why we get here that a and b as the co-prime numbers, but we have proved that they are not co-prime, and that is because of our wrong assumption that root 2 is a rational number. So we are concluding that root 2 is not a rational number, it is an irrational number. Okay, and we are going to the examples. Here next is to prove that root 3 is an irrational number. We can use the same steps. In the previous case we prove that root 2 is a irrational number. First we are going through the wrong assumption that root 3 is a rational number. If root 3 is a rational number, it can be written as the p by q form, and we are just taking as r by s as in the previous case, and cancelling with their common factors, we are getting root 3 is equal to some integer a by b, and now these a and b are co-prime to each other. They have no other common factor other than the number 1. And now we are taking this equation here, b here, taking here we get b root 3 is equal to a, and squaring both sides we get the square of root 3 is 3. Okay, and here b square and here a square, and we get 3b square is equal to a square. And look at this, what we can get, 3 divides the a square, and if 3 divides a square, 3 divides a also from the first theorem. Okay, if 3 divides a, that means 3 is a factor of a. Okay, let it be. And a is a multiple of 3, isn't it? So we are taking a is equal to 3c, c some integer, and substituting this value of a in this equation, we get 3b square is equal to 9c square. A square is 3c, and 3c the whole square, we get 9c square. And cancelling this 3 and 9, we get b square is equal to 3c square. Okay, and from this we can get that 3 divides b square, and if 3 divides b square from the theorem, we know that 3 divides b also. Okay, that means 3 is a factor of b. And we get here that 3 is a factor of a and b. That is, they have the common factor 3 other than the number 1. So they are not co-prime. But we have get here that they are co-prime. That is because of our wrong assumption that root 3 is a rational number. So we can conclude that root 3 is not a rational number and it is definitely an irrational number. Okay. We can go to the next example. Show that 5 minus root 3 is a irrational number. Okay. And as usual, we are going to assume in a wrong way. That is, 5 minus root 3 is a rational number. If 5 minus root 3 is a rational number, it can be written as the p by q form. We are taking some r by s and cancelling their common factors, we get a by b. And this a and b are some co-prime, are co-prime to each other. Okay, and now 5 minus root 3 is equal to a by b, and taking this root 3 here, we get 5 minus a by b equal to root 3. That is, and when cross multiplying this, we get 5b minus a by b. And we know that 5b and a all are some positive integers, and definitely this form is a rational number. And if this 5b minus a by b is equal to root 3, then as this is a rational number, then this root 3 also will be a rational number. But we have proved that root 3 is an irrational number. Then why we get like this? That is because of our wrong assumption that 5 minus root 3 is a rational number. So we are concluding here that 5 minus root 3 is not a rational number and it is an irrational number. Okay. Going to the next example, that show that 3 root 2 is an irrational number. As usual, we are going through the wrong assumption that 3 root 2 is a rational number. Let it be a rational number, and it can be then written as the p by q form, that is some r by s, and we are cancelling with their common factors and we are getting some co-prime integers like this. And now 3 root 2 is equal to a by b, where a and b are some co-prime numbers. Okay, co-prime to each other. Here we are taking root 2 and 3 here, and root 2 is equal to a by 3b. And look at this, a, b and 3 are some positive integers, and this form will be definitely a rational number. And if this is the rational number, then this root 2 will also be rational number because it is equal to each other. But we have proved that root 2 is a irrational number. Then why we get here this? Because of our wrong assumption that 3 root 2 is a rational number, and we are concluding that 3 root 2 is not a rational number and it is definitely an irrational number. Okay, we can stop here now, and don't forget to subscribe and share this channel with your friends if you like this. And if you have any suggestions and doubts, you can mail me at friend4maths@gmail.com. Okay, till then, take care, bye.